Black holes get most of the attention. They bend light, they swallow stars, they hide behind darkness so deep that not even light can escape. But somewhere in the galaxy, there are objects much smaller than black holes, much smaller than our sun. Objects only about the size of a city, and yet they may be some of the most violent dead stars in the universe. They are called magnetars. A magnetar is not a normal star, it is not a planet, it is not a black hole. It is the collapsed core of a massive star after death. When a giant star reaches the end of its life, it can explode in a supernova. The outer layers blast into space. But when the explosion is over, something remains: the crushed core. If the core is massive enough, it may collapse into a black hole. But if it stops just before that final collapse, it can become something else. A neutron star. A neutron star is one of the densest objects known to science. It can hold more mass than the sun, squeezed into a sphere only about 12 to 15 miles wide. That means you could fit something heavier than the sun inside an area smaller than many cities on Earth. The gravity on its surface is almost impossible to imagine. The matter inside is packed so tightly that normal atoms cannot survive. Electrons and protons are forced together, creating neutrons. This is already extreme. But a magnetar takes that extreme and pushes it even further. A magnetar is a special kind of neutron star with an unbelievably powerful magnetic field. That is what makes it different. That is what makes it dangerous. And that is why a dead star can still hold impossible power. To understand why magnetars are so strange, we have to begin with the death of a massive star. For millions of years, a giant star burns through its fuel. Deep inside, nuclear reactions push outward while gravity pulls inward. For a long time, those forces balance each other, but eventually the fuel runs out. The star can no longer support itself. Gravity wins. The core collapses in an instant. Then the outer layers explode outward in one of the most powerful events in the universe, a supernova. For a brief moment, one dying star can shine brighter than entire galaxies. But after the explosion fades, the story is not over. The crushed core remains. That core can become a neutron star, and in rare cases, it can become a magnetar. Earth has a magnetic field. It helps protect our planet from charged particles from the sun. It helps compasses point north. It surrounds us quietly every day. But compared to a magnetar, Earth's magnetic field is almost nothing. Even a normal neutron star can have a magnetic field trillions of times stronger than Earth's. A magnetar can be about 1,000 times stronger than that. That means a magnetar is not just magnetic. It is magnetic on a scale that breaks our everyday understanding of the word. This magnetic field is so powerful that it controls the behavior of the star itself. It stores incredible energy. It twists, it strains. It pulls on the crust of the dead star, and eventually something has to give. The surface of a neutron star is not like the surface of Earth. It is not soil, rock, ocean, or ice. It is an incredibly dense crust wrapped around a dead stellar core, but even that crust can crack. When the magnetic field of a magnetar becomes too stressed, it can twist the star's surface until the crust suddenly shifts. Scientists call this a starquake. On Earth, earthquakes happen when pieces of our planet's crust move along fault lines. On a magnetar, the crust of a dead star can crack under the pressure of a magnetic field beyond anything we can create. And when that crack happens, the result is not just a rumble. It can release a burst of X-rays and gamma rays powerful enough to travel across the galaxy. For most of human history, we had no idea these objects existed. The universe was already strange enough with planets, comets, stars, galaxies, and black holes. But then, astronomers began detecting sudden bursts of high-energy radiation from deep space. They were not steady like normal stars, they repeated. They flashed, they vanished. Then they came back again. Some of these objects became known as soft gamma repeaters because they released repeated bursts of gamma rays. Eventually, scientists realized that some of these mysterious signals were coming from magnetars. dead stars with magnetic fields so extreme that they could power violent explosions. And one Magnetar event became especially famous. On December 27, 2004, a wave of radiation reached Earth. It came from a magnetar known as SGR 1806-20. The object was far away, tens of thousands of light-years from Earth on the other side of the Milky Way. That means the explosion had actually happened long before humans ever detected it. The radiation had been traveling through space for thousands of years. Then, in 2004, it arrived. For a fraction of a second, the burst was so powerful that satellites detected it immediately. The flare was one of the brightest events ever recorded from outside our solar system, and even from its enormous distance, it affected Earth's upper atmosphere. Think about that. A dead star far across the galaxy cracked and Earth noticed. That is the kind of power magnetars can release. The event did not destroy Earth, it was far too distant for that. But it showed scientists something incredible. Magnetars are not quiet stellar fossils. They are unstable, active, violent remnants. They may look tiny compared to stars and galaxies, but inside them is a reservoir of magnetic energy that can erupt without warning. This is what makes them so fascinating. A black hole is terrifying because it is dark and final. Cross too close and nothing comes back. But a magnetar is terrifying in a different way. It does not need to swallow you. It does not need to be large. It does not even need to be close to release energy on a scale that reaches across space. Its danger comes from what it is, a dead star under impossible pressure, wrapped in an invisible magnetic field stronger than almost anything else in the known universe. If you could somehow approach a magnetar, the magnetic field would dominate everything around you. Long before reaching the surface, ordinary matter would be under extreme stress. Atoms themselves could be distorted by the field. Chemistry, electronics, and normal matter would not behave the way they do on Earth. A magnetar is not just a place. It is an environment where the rules of familiar reality are pushed to the edge. And yet, magnetars are not science fiction. They are real. Astronomers have found magnetars in the Milky Way. They have also found signs of them far beyond our galaxy. They are rare, but they are real. Most neutron stars do not become magnetars. That is one of the mysteries. Why does one collapsed stellar core become a regular neutron star, while another becomes a magnetar? The answer may have to do with the way the star collapses, how fast it spins when it is born, and the conditions inside the supernova. A magnetar may begin its life spinning rapidly. Powerful forces inside the newborn neutron star may amplify its magnetic field. But even after scientists identify the possible ingredients, the full story is still difficult to understand. Because magnetars are not easy to study, they are distant, they are small, they do not behave predictably. For long periods a magnetar may seem quiet, then suddenly it erupts. A burst of radiation flashes across space. A starquake cracks the crust. A giant flare releases more energy in a blink than our sun produces over enormous stretches of time. Then the magnetar fades again, leaving astronomers to study the afterglow and search for clues. This is one reason magnetars are so important. They may help scientists understand some of the most mysterious signals in the universe. High-energy bursts, strange flashes, sudden blasts from galaxies far away. Some of these events may be connected to magnetars or to objects like them. They may also help scientists understand how matter behaves under pressure that cannot be recreated on Earth. No lab on Earth can build a neutron star. No machine on Earth can create a magnetar's magnetic field. So the universe becomes the lab. Every burst is a clue. Every flare is a message. Every strange signal tells us something. It points toward physics at the edge of the possible. But perhaps the most haunting thing about magnetars is how small they are. When we imagine cosmic power, we usually imagine size, giant stars, supermassive black holes, vast galaxy, huge blasts that stretch across many light years. But magnetars prove that the universe does not always hide its greatest power in the largest places. Sometimes power is compressed. Sometimes the most extreme object is not the biggest one. It is the one where gravity, magnetism, and death have been squeezed into a space smaller than a city. A magnetar is the remains of a star that died violently, but it is not peaceful. It is still changing, still cracking, still releasing bursts of energy into the dark, a dead star that refuses to go quiet. Somewhere in the Milky Way, magnetars are turning slowly in the darkness. Their surfaces are crushed, their magnetic fields are twisted, their interiors are locked under pressures we can barely describe. And every so often one of them breaks. A flash races outward, across dust, across stars, across thousands of light years. And long after the dead star cracked, the signal reaches us, a reminder that the universe is not silent. It is full of hidden violence, full of impossible objects, dead stars with power beyond imagination. Black holes may be the monsters we fear most, but magnetars are something different. They are smaller, stranger, and in their own way, just as terrifying. Because in the darkness between stars, a dead sun can still scream, and when it does, the galaxy hears it. This is Hidden Science Stories HQ.